Welcome back to AI.Code.Cast. I am so excited for this deep dive, you guys. It's going to be a good one. We're going to be tackling a classic coding problem. And it's not just fun to solve, but it's also like super relevant to what we do here, with AI and language processing. Get ready to group some anagrams.
Ah, yes. The group anagrams problem. It's a great one for really sharpening those algorithm skills and understanding, how to make code efficient.
Okay, so for our listener who might be new to this, can you quickly lay out the challenge? What exactly are we trying to accomplish here?
Absolutely. So imagine you have this big jumbled list of words, right? Your mission, should you choose to accept it, is to write code that neatly sorts these words into groups where all the words in a group are anagrams of each other.
And just as a reminder, an anagram is basically a word or phrase that you create by rearranging the letters of another word or phrase. So listen and silent are anagrams.
Exactly. So if our list has listen, silent, and list, and maybe some other random words in there, our code should be smart enough to put those three together in a group because they're all anagrams.
Got it. So let's say I'm staring at this problem for the first time. Where do you even begin to approach something like this?
Well, a common first instinct is to think about a brute force approach. It's not always the most efficient way, but it can be a good way to wrap your head around the problem.
Okay, so brute force.
hmm
Help me out here. What would that look like for grouping anagrams?
So it would involve a lot of comparisons. You'd basically take each word on your list and then you'd compare it to every single other word to see if they're anagrams or not.
Okay, I can see how that would work. But wouldn't that be super slow, especially if you have a humongous list of words?
Exactly. That's the main drawback of brute force. The number of comparisons that you need to make grows really fast as your list gets bigger. We're talking about a time complexity of O of n squared, where n is the number of words. So yeah, not ideal for efficiency.
All right, so brute force is out. What's a smarter approach? I'm guessing we don't want to be comparing every word to every other word. It's got to be a more elegant way.
There is. And this is where things get interesting. What if, instead of comparing the words directly, we find a way to represent them so that anagrams have the same representation?
That's an interesting thought. But how do you represent a word in a way that captures its anagramness?
Well, think about what makes two words anagrams. They use the same letters, right? So what if we sorted the letters of each word alphabetically?
Okay, I see where you're going with this. Silent and listen both become illness when you sort their letters. So if we sort every word in our list, anagrams will have the same sorted form.
You got it. And now, instead of comparing every word to every other word, we can just compare their sorted forms. And that simplifies things a lot.
This is clever. But how do we actually use this to group the anagrams? It's not like we can just have this giant list of sorted words and magically know which ones belong together.
You're right. And that's where a really powerful data structure comes in. The dictionary, also known as a hash map in some languages.
Dictionaries. I mean, we use those all the time here at AI.Code.Cast, but I'm a little fuzzy on how they'd help us group anagrams. Can you break it down for our listener?
Sure. So imagine a dictionary not for looking up definitions, but for organizing our anagrams. The sorted form of a word becomes the key in our dictionary, and the value that's associated with that key is a list of all the original words that have that sorted form.
So let's say we have the words eat, tea, and tan in our list. Walk me through how we'd use a dictionary to group them.
Okay, starting with eat, we sort it to get a eat. This a eat becomes a key in our dictionary. And since it's the first time we're seeing this key, we create a new entry in our dictionary with a eat as the key and an empty list as the value. Then we add eat to that list.
Got it. So now we have an entry in our dictionary where eat points to a list containing just eat.
Right. Now we move on to tea. We sort it, and surprise, surprise, we also get a eat. But since a eat is already a key in our dictionary, we don't create a new entry. We simply add tea to the existing list that's associated with the a key.
So now our dictionary has at pointing to a list containing both eat and tea. They're grouped together. What about tan?
Well, tan sorts to ant. This is a new key, so we create a new entry in our dictionary with ant as the key and a new list containing just tan as the value.
Okay, I'm totally getting this now.
Yeah.
Each unique sorted form becomes a key, and all the words that share that sorted form get grouped together in a list under that key. That's a really elegant way to organize things.
Exactly. And what's even better is that this approach is much more efficient than that brute force method we talked about earlier.
Yeah, that's what I was thinking. But I'm curious, how much more efficient is it? I know sorting takes some time too.
You're right. Sorting does add some computational overhead, but it's not as bad as you might think. The time complexity of this approach, where we sort the strings and use a dictionary, is O of nk log k, where n is the number of strings and k is the average length of those strings.
Okay, break that down for me. What's that log k doing in there?
The log k factor comes from the sorting step. Most efficient sorting algorithms have a time complexity that involves a logarithmic term. It's a bit technical, but the main takeaway is that sorting is relatively fast, especially compared to that n-squared complexity of our brute force approach.
Right. So even though we're adding this sorting step, it's still way more efficient than comparing every word to every other word. And this whole dictionary setup just seems so much cleaner and organized.
It is. But it's always good to be mindful of the trade-offs. Using a dictionary to store all these words in their sorted forms does take up space. The space complexity of this approach is O of nk. That means the amount of memory we need grows linearly with the number of words and their average length.
Okay, so that's something to keep in mind. It's a super efficient approach,
Hmm?
but it does come with a bit of a space cost. I guess if we're dealing with truly massive amounts of data, that could become an issue.
Precisely. And that makes me wonder, are there other approaches that might strike a different balance between time and space complexity?
Ooh, that's a great question. Is there a way we could perhaps achieve even faster time complexity, maybe even linear time? And is there a way to do it without sacrificing too much space?
You're thinking along the right lines. What if instead of sorting the letters, we could somehow capture the essence of a word's anagramness without changing the letter's order at all?
Without changing the order. What else could we use to identify anagrams? I mean, they use the same letters, but the arrangement is what's different. What else is there?
Think about it this way. Anagrams have the same letters, just in different amounts. So what if we focused on those amounts, like the frequency of each letter? It'd be like a fingerprint for each word based on its letter counts.
Ooh, a fingerprint. I like that.
Correct.
So instead of looking at the order of the letters, we're looking at how many times each letter appears listen and silent would have the same fingerprint because they both have one L, one I, one S, one T, one E, and one N.
Exactly. And the beauty is we can represent these fingerprints in a really compact and efficient way. Remember those 26 element arrays we sometimes use here at AI.Code.Cast? Those come in handy here.
Wait, are you suggesting we use a 26-element array to represent the letter counts of each word? That sounds familiar, but I need you to help me connect the dots on how that helps us group anagrams.
Absolutely. So imagine each element in this array corresponds to a letter of the alphabet. The first element for A, the second for B, and so on. For each word, we go through it letter by letter and increment the count in the corresponding element of the array.
Okay, starting to see it. So for the word T, we'd increment the count in the T position, the E position, and the A position. That array becomes the fingerprint for T.
Precisely. And the array for eat would end up being identical because it has the same number of T's, E's, and A's.
So we can use these 26-element arrays as keys in our dictionary. Just like with the sorted strings, we group the words under the same key if their arrays are identical. That means they're anagrams.
You got it. And here's the kicker. Since we're not sorting the letters anymore, we've significantly improved our time complexity. This approach has a time complexity of O of nk, where n is the number of words and k is the average length of a word.
Hold on. O of nk. That's linear time complexity. So we've gone from O of n squared with brute force to O of nk log k with sorting, and now down to O of nk. That's a massive improvement, especially when you're dealing with tons of words.
Exactly. And it's all thanks to this clever idea of using character counts as like a proxy for identifying anagrams.
I'm impressed. But what about the space complexity? We're still using a dictionary, and now we have these arrays to store as well.
You're right to bring that up. The space complexity is still O of nk. We're essentially storing all the original words plus their corresponding arrays in the dictionary.
So we're trading off a bit of space for a big gain in speed. That's a classic trade-off in coding, isn't it? Sometimes you have to prioritize one over the other.
Absolutely. And the best choice often depends on the specific needs of your application. But overall, this character count approach is a powerful technique to have in your arsenal.
It definitely is. Now, I have a question about these arrays. It seems a bit arbitrary that we're using arrays with 26 elements. I mean, couldn't we use a different data structure to store those character counts? Maybe something smaller or more tailored to the specific words we're dealing with.
That's a fantastic question, and it shows you're thinking critically about optimization. You're right, we could potentially explore different data structures or representations. Maybe a bit vector could work where each bit represents the presence or absence of a particular letter. Or we could even think about using a hash function that's specifically designed to generate unique values for anagrams based on their character counts.
Wow, so many possibilities. It's exciting to see how even a seemingly simple problem like grouping anagrams can lead to such a rich exploration of data structures and algorithms.
It's all about finding the right tool for the job. And that's a big part of what we do here at AI.Code.Cast, right? Always experimenting, always trying to find the most efficient and elegant solutions for the challenges we face in AI and language processing.
Absolutely. I'm feeling inspired to go tinker with some code now and see if I can come up with some creative variations on these solutions. But before I run off to my code editor, I'm curious to hear your thoughts on comparing these two main approaches we've discussed today, sorting strings versus using character counts. What are the key takeaways for our listener? All right, so we've explored these two really cool approaches to grouping anagrams, right? We've got sorting the strings, and then we've got using these character counts. Both of them are clever in their own way, and both are definitely way more efficient than that brute force method we talked about. But like, if I'm here at AI Codecast and I'm faced with this problem in like a real project, how do I choose the best weapon in my coding arsenal?
It's like choosing the right tool from your toolbox. You wouldn't use a hammer to screw in a light bulb, right?
Yeah.
The best choice really depends on the context.
Okay, so context is key. What kind of factors should I be considering when I'm making this decision?
Well, the size of your data set is a major one. If you're dealing with a relatively small list of words, like a few hundred or even a few thousand, the difference in performance between the two approaches might not even be noticeable.
So if it's a smaller project and I want to keep things simple and easy to understand, maybe the sorted string approach is a good bet.
Exactly. It's very intuitive, and the code is usually quite straightforward. However, if you're working with those massive data sets we often encounter here at AI Codecast, then things are a bit different.
Right, because when you're dealing with millions of words, even small differences in efficiency can have a huge impact on processing time.
Absolutely. And that's where that character count method really shines. Its linear time complexity makes it a powerhouse for those larger data sets. It's like having this super fast sorting machine that can just handle anything you throw at it.
Okay, so big data equals character counts. But we also have to think about memory usage, right?
Hmm.
Especially with those giant data sets.
You're spot on. Both approaches have a space complexity of O of nk, meaning the amount of memory they use grows linearly with the number of words and their average length.
So in terms of memory usage, they're pretty much on par with each other.
In theory, yes. But in practice, there might be subtle differences depending on the specific programming language you're using and how you actually implement the dictionary. Sometimes those little implementation details can have a noticeable impact on performance.
So there's always a good idea to do some testing and see how different solutions behave with your specific data.
Absolutely. Experimentation is key. And you never know, you might even discover some creative optimizations or like hybrid approaches that combine the best of both worlds.
Ooh, a hybrid approach. Now that's an intriguing thought. Maybe there are cases where you could use elements of both sorting and character counting to get even better results.
That's the beauty of coding. There's always room for creativity and innovation, and that's what keeps things exciting.
I couldn't agree more. This deep dive has been such a fantastic reminder that understanding the nuances of different algorithms and data structures is essential for any coder, but especially for those of us working in AI.
And remember, even seemingly simple problems, like grouping anagrams, can be springboards for exploring deeper concepts and really honing those problem-solving skills.
Well said. So to our listener, I hope you've enjoyed this journey into the world of anagrams. We've gone from brute source beginnings to these really elegant solutions. We uncovered the power of dictionaries and like the importance of choosing the right approach for the job. And who knows, maybe this deep dive has sparked some new ideas for your own coding adventures. Thanks for joining us on AI Codecast.